Good morning, everybody. Well, thank you, Ronald. Thank you, Corey. Thank you, Ernesto. Thank you. Thank you. All right. Um, thank you, everybody. All right. Well, today I want to start a new chapter. And this new chapter is about integration, integration of complex functions, of course. But before uh, talking about integration of complex numbers, I would like to somehow review the whole concept of integration that you learned in Calculus 1, 2, and 3. Okay. So in Calculus 1, we started with just integrating a function of one variable from interval A to B. And the geometric interpretation was this is going to give us the area under the function between those two vertical lines A and B. In Calculus 2, we integrated, or we had the double integration. And this double integration of a function of two variables. Remember, a function of two variables, geometrically, z equal f of xy represent a surface. And this one, when of course f is non-negative, the geometric interpretation was we are finding a volume of a solid whose base is some part of plane, and on the top is bounded by the surface. Well, later we talked about triple integral, and if you need to integrate a function of three variables. But unfortunately, in this case, we don't have a geometric interpretation, right? Because it has to go to 4 dimension, and we cannot we at least visualize 4 dimension. However, we had a interpretation from physics point of view. You have a solid S, and it is made of some sort of alloy that at different places has different density. Assuming that this function gives us the density at different points, this triple integral will give us the mass of that solid, all right? The mass of that solid. Well, later in Calculus 3, you learned about line integral, where you were integrating over a curve. C is a curve, all right? But we call it line integral. Of course, there are some other types of integrations. We had a line integral of, for example, a vector field, which from physics interpretation is the work done when you apply this force to an object, and you try to move that object along a curve, okay? That's called the work done. Oh yeah, there are, here is the what I basically meant. So you have a curve given, this curve C, and you have an object. You apply this force F to this object, right? And move this object from point A to point B. And what this line integral of vector field, the result is the work done. All right, and here is how we compute this. The vector field has two components here, P and Q. So it is P dx plus Q dy, which it goes back to line integral of a function. Well, there are, of course, other types of integration, surface integral, and but the common fact, when you look at all these different types of integrations, the common fact is that you have a function and you have either an interval or a curve or a solid or a part of plane, and you want to integrate over those. So here is how the integration works, starting with the calculus 1. And the rest of them will follow the same pattern, by the way. In calculus 1, you want to have a, let's say, nice function, real valued on that interval, and you want to integrate. Now, what is that integration? Well, as I said, geometrically, it means the area under this curve bounded by this interval AB. So the first step in doing the integration, in all sorts of integration, right? I'm just concentrating on this one. You partition this interval. Partitioning this interval like this, putting more points, basically means the object that we want to study, we will slice it, okay? We will slice that object, and then we will estimate any slice. So a typical slice like this, you choose a point here and multiply the length of this interval by the value of function at this point, and you will get area of this rectangle, right? In this case, you get area of that rectangle. So here is choosing a point in this typical partition or a slice and forming this product, F evaluated at this point multiplied by the length of that interval. This is done for one of the partitions, one of the slices. You do for all of them and add them up. When you add them up, you get this thing, which is called Riemann sum. Okay, that is called Riemann sum. Now, if you want to find the area under the curve, this Riemann sum, which is the area of this rectangle or rod adding together, will not be exactly what we are after. So the question is, how do we get the exact area here? Oh, we get the exact area when we make these slices thinner and thinner. How thin? As thin as possible. And that is the idea of taking limit, putting infinitely many points in this partition, all right? When I say infinitely many points, that is the concept of limit. We are using the concept of limit. So, and you take limit, and if the function is a nice function, the limit exists. And that limit is what we call integral of the function. All right, that number, as a result of this limit, you get a number. That number is denoted by this symbol. So whenever you see this symbol, that means you got to go through this partitioning, evaluating each slice, putting them together. All right, this is integration. A slice the object that you are trying to study. Study each slice and put them together and make those slices as thin as possible. So that is the way integration was introduced. Of course, we had a bunch of facts that can be proved easily, and you have seen it in calculus. One of those facts, of course, is fundamental theorem of calculus, which somehow correlates the idea of this definite integral and the concept of antiderivative, all right? So, and that fundamental theorem of calculus, which is this fundamental theorem of calculus, basically says if you're dealing with this function and you have its antiderivative, let's say capital F is antiderivative. Antiderivative means if you take its derivative, you get this function. If you have one of the antiderivatives, then fundamental theorem of calculus is in fact finding a relationship between antiderivative and this concept of integration. It says, all right, if you want to calculate this, you don't have to go through that process. It is just the antiderivative evaluated at b minus the antiderivative evaluated at a. Okay. This is for very good reason. It's called fundamental theorem of calculus because it sort of finds a relationship between the concept of antiderivative and the concept of definite integral. All right. So a quick review of integration, and in all different sorts of integration, this is what we do. We partition and then put everything together, all right? And here is another fundamental theorem of line integral. When you integrate a vector field. Now, this fundamental theorem of line integral, remember, this is different from the other fundamental theorem of calculus. This only applies to vector fields. It says that these three statements are equivalent. Statement number one, the vector field that we are dealing with is conservative, which means that it's a gradient of a function. And if this happens, then the integral over the curve going from point A to point B is independent of path of integration, is independent of that curve. Doesn't matter which curve we choose from point A to point B. In fact, we know its values will be just the potential function when it is conservative, right? Potential function evaluated at endpoint minus evaluated at initial point, all right? And then the third one that is also equivalent to this, which this constitutes the fundamental theorem of line integral. It says if you are integrating on a closed curve, then you are going to get zero. Okay? Okay. Now, in complex, here is what we did for line integral of a function. So I'm just going through line integral of a function the same way that we went through just finding the area. So you have a function defined and a curve is given. So you partition this curve, and on a particular slice, let's say on this one, on this slice, on this little slice, choose a point. All right, this point will be x of t star y. Evaluate the function that we are going to integrate at this point, then multiply by the length of this little curve. Oh, this is the arc length little arc length, all right? So that is what you get, evaluating the function and multiplying by that little arc length. That gives you for this particular one. You add them up. You do for all those little things and add them up, and this is what you get. This is, again, a Riemann sum. And you then take the limit as the number of partitions approaches uniformly to infinity. And you get a number, if you are lucky, if the integral exists, you get a number. Sometimes the limit does not exist, okay? So that number is denoted by this. Okay, that number is denoted by this. All right. See, everything, all those sorts of integration that you have seen so far, all go through the same process. Partitioning, evaluating function at a particular point, multiplying by whatever, and then forming the Riemann sum, taking limit. And if the limit exists, that is called the integral. In this case, it is the line integral. Okay. So, so far so good. And now I'm going to talk about complex integration. Good news. In calculus, you have different types of integration, right? you had just single integration in calculus 1. In calculus 3, you had double integration, triple integration, all right? Curve integral, line integral. But in complex, we only have one type of integration. And always we integrate over a curve, okay? Good news. In complex, only we integrate over a curve. So yeah, a curve is given. Here is a curve. Sometimes we call it just ZT, okay? Remember, for each T, this is going to give us a point, an ordered pair. You just join those ordered pairs, you will get a curve, all right? So sometimes we simply say Z of T and write it this way, Z of T, xt plus iyt. So you have a curve. For example, you might have a circle, okay? A circle of radius 0, radius r, centered at 0. Oh, how do we denote that? Okay, here is a circle of radius r. For different t's, you get different points of that circle. Well, we can use Euler's identity and write this way. So when t goes from 0 to 2 pi, you will cover the whole circle, all right? So depending on which part of the circle you want to cover, if you want to cover just the portion in the first quadrant, then t will go from 0 to pi over 2, and so on. All right. Here is a circle of radius r, but centered at a point z naught. Okay. All right. So a curve is given. It could be a circle. It could be something else. Here is a curve. And you have a function of complex variable. So we go through the same process. We partition this curve, okay? We partition this curve. At a typical partition, let's say this. At this typical partition, we choose a point, right? Z star k. Evaluate the function at this point and multiply by the length of this curve. So here, and then, of course, this is a typical one. Do it for all the slices. You will get this. We call this one again Riemann sum. And then you take limit as the number of partitions approaches infinity uniformly. If this limit exists, we call it integral of f of z, okay? If the limit exists and is a number, that number is denoted by this. So the foundation, the underlying process is the same. It's like calculus 1, calculus 3. It's the same. You partition, evaluate the function, multiply by this. Basically, you slice things and concentrate on one slice, estimate that one, and then put them together. Put them together, you get this sum. And let the number of partitions approach infinity. Okay, good. So now, of course, the question is, how do we calculate these things? Well, I'm going to talk about practicality. This was the theory, how the complex integration is defined. But before going to the computation and examples, I'm going to, based on just what I said right here, I'm going to discover an inequality. Okay. That inequality is going to be extremely important. And we will call that inequality ML inequality, as you will see. So the question is, what if the function that we are going to integrate, this one, on this curve is bounded? The modulus of function, let's say, is bounded, okay? If the function is bounded, this function on the curve, how big the modulus of this complex number is going to be? How large the modulus of this complex is going to be? Well, this is what I'm going to talk about next, which is called ML inequality. All right. So suppose on that curve, the function is bound. Oh, please remember, in complex, we don't have inequalities for complex numbers. For modulus, when you take the modulus, you get a real number. For that one, we can talk about the inequality. All right. So suppose f of z is less than or equal to m. Then I want to prove that the integral has an upper bound, modulus of integral. It's less than or equal to m. M is this one. L is the length of this curve over which we are integrating. And here is why. Here is the justification. Oh, remember that Riemann sum? Here is the Riemann sum, right? So modulus of this is less than or equal to, we take the modulus inside. But this is less than or equal to m. Oh, I replace this by m, I get something a little bit bigger. So here is m. I can pull, now this is a constant. I can pull this constant out. Then you are dealing with, on the left is the Riemann sum. On the right, you get this one. But remember, these are those little pieces of the curve we are putting together. As p approaches, I mean, the number of partitions approaches infinity, this is going to give us the length of that curve. Okay? And this one, when you take limit, is going to give us the integral. So as the norm of partition approaches zero, or another way, the number of points we are inserting approaches infinity uniformly, This is what you get. And this is called ML inequality. All right? Any question about ML inequality? Any questions so far? Okay, thank you, Corey. Okay, now I'm going to give you an example in which we are using ML inequality. Let's say, remember, ML inequality is good for finding uh, an upper bound for this integral. Tells us how large this integral can get, the modulus, of course. So here's an example. Find an upper bound here for this one. The function f is this, and the curve is the unit circle with y being positive, right? This is the way we say unit circle. All the z's that modulus is 1. So all the points on the unit circle. But there's another restriction. It says y is positive, so upper half. So this is the curve. So here's the function. We are integrating over this curve. Okay. Well, the length of this curve, we know what it is. That is L. When the radius is 1 and the perimeter of a circle is 2 pi r, right? 2 pi r. Here, r is the radius. So 2 pi will be the whole circle. So the upper part, just the length here, is pi. How about m? Remember, m is upper bound for this one when you choose z to be on this, when you choose z to be modulus of z1. Well, for that one, we are going to use triangle inequality. There are two triangle inequalities. One is this one. Triangle inequality 2 is this. You use this one for numerator. Use this one for denominator. So here is a function for numerator. Well, to begin with, the modulus of a fraction is modulus of top over modulus of bottom. But this is top is less than or equal to modulus of this plus modulus of this. For denominator, we use number 2. So for this one, modulus will be bigger than or equal to this. And when we make the fraction smaller, the denominator is smaller, the fraction becomes bigger. Right now, you use the fact that modulus of z is 1. So here is 1, here is 1, here is 1. So m is 3. How about the and L, of course, I already told you that is perimeter, is pi. Therefore, the largest, that's the upper bound for this modulus of integral is ml. So the value here cannot exceed 3 pi. Cannot exceed 3 pi. All right. This is good to know. This is a very good information to know. All right. Any comment about this example? It's a very important example. And especially it's important to understand that how to use those two triangle inequalities. Okay. More examples coming. Right here is how to evaluate. You are dealing with this integral, right? How to evaluate that integral? Well, if we write f of x, its real part plus I, imaginary part, and dz, which is dx plus I dy, all right? So this is what we get in the Riemann sum, of course. This is what we get. Now you multiply and then separate the real part and imaginary part. The next thing you want to do is take limit as the number of partitions approaches infinity, all right? This will give you the integral. But how about this? This will give you u dx minus v dy, I v dx, u dy. So that is a very interesting way to look at the complex integration, okay? Complex integration. Now, I proved this one. I sort of gave you justification for it, but we didn't have to go through this. If you could think about it as saying that, look, I am going to integrate over this curve u plus iv dz, z is x plus iy, so dz is dx plus I dy. If you multiply and you separate real part and imaginary part, you get exactly the same thing, okay? Exactly the same thing. The advantage of having this is it goes to calculus 3 because u is a function of two variables, v is a function of two variables, all right? Same thing here. And we can use those facts and that we learned in calculus, right? Okay, keep this in mind. Keep this in mind because later, when I am going to talk about Cauchy's theorem, I will use exactly this equation to show that if, for example, C is a closed curve and the function is a nice function, you will get 0. That's the Cauchy's theorem, okay? Keep this in mind. Now, how do we use this? Here is how. Suppose the function is this function. You want to integrate over a curve, and the curve is given by y equal x squared. It's a parabola, sort of parabola, but it says from 0, 0 to 2, 4. So this portion of parabola, this portion of parabola. You're going to move from here, go to this point. Well, One way to take care of this is to parameterize this curve to find the equation of that curve in complex. And in this case, it is not that bad. Anytime the curve is given as y equal f of x, the parameterization is t plus f of ti. Okay? So this is parameterization. So this is the real part. This is the imaginary part. The formula that I just told you, here is f of z, u plus iv. But since we are integrating over this curve, your x is t, your y is t squared. It will be 2t plus it squared dz. What about dz? Oh, well, here is z. dz is z prime dt. Here is z prime dt. So you multiply out and integrate. So one way to integrate directly is finding the parameterization and replacing x by x value of parameter. And what maybe I should sort of tell you here that, look, any point along this curve, x is t and y is t squared. And when you integrate, actually, you restrict the value of this function over this curve. So we don't want the function at this point or this point, right? Only along this curve. So you replace x by t, y by t squared. And that's what you get. That's what you get. And here is z prime dt. All right? So if you can parameterize, of course, I leave the evaluation to you. If you can parameterize the function, the curve, this integral c f of z dz is basically from a to b, the value of parameters, f of z of t, and that's what I did here, right? This is, in fact, f of zt. Then here, z prime of t dt. All right. If you can find parameterization of the curve, so integration over the curve is this. And that's the example. Okay. Now I need to give you more examples, especially very important examples. Here is another one that we really love and we will use it a lot. Oh, this is something that you definitely should memorize it. So the function that I'm integrating here is 1 over z. I want to integrate this one over this curve. What is this curve? This is the unit circle. All right, the unit circle is right here. Every point on the unit circle is this. So this is z of t. F of z of t means replace z by z of t, which is right here. Then z prime. Z prime is I e to the it dt. So this cancels. You have 0 to 2 pi I dt, and that's 2 pi I. So if you integrate dz over z over the unit circle, this is what you get. It doesn't have to be unit circle. It could be any circle. It could be a circle of radius a, right? Instead of unit circle, it could be a circle of radius a. In this case, z of t becomes a, the radius, e to the it. And when you apply the same formula, a and a cancels, again, you are going to get 2 pi I. All right? So either you integrate over a unit circle or any other circle of radius a centered at 0, you will get always 2 pi I. How about if we integrate over this circle whose radius is 1? So radius is irrelevant here. But center is z naught. In this case, you integrate over dz over z minus z naught, all right? You get, again, 2 pi I. Again, you get 2 pi I, all right? This is one of the very important integrations that we will see it very often. And I would say is an extremely important one. So, one more time, let me emphasize this. If you integrate this guy, dz over z, over a circle of radius doesn't matter. That's why we get unit circle. You get 2 pi I. Okay? You get 2 pi I. How about if there is a, instead of z, there is an exponent here? What happens if we have an exponent there? Well, let's look at that. Let's look at that when we have an exponent right there. Let's say z to the n. But I know that it is not dz over z. So n is not -1. Other than -1, anything can be. Even any negative integer you can have here other than -1. Okay? So in this case, again, I'm integrating over this unit circle. And this is the parameterization of unit circle. So you replace z by e to the it. z prime dt. Well, this I is a constant, you can pull it out. And here you get e to the I, just add the exponent, n plus 1t. I know that n is not -1, right? This is not like 0 then. We already took care of -1. Now, the antiderivative here is right. So it goes from 0 to 2 pi. If you plug 0, you get 1. If you could plug 2 pi again, you get 1. So you get 0. So what is the conclusion? Here is the conclusion. The integral of Zn dz over a unit circle is 2 pi I when n is -1. It is 0 when n is different from -1. Doesn't matter what, just different from 0. Anything else will give you 0, but -1, which is dz over z, will give you 2 pi I. All right, that's very, very important integration we should keep in mind. All right, so I will stop at this point. That will cover section 14.1, and section 14.2 is about Cauchy integral theorem. And Cauchy's integral theorem basically says, if you have a nice function where derivative exists and is continuous, then integration over a closed curve is 0. Okay? But the proof of this uses Green's theorem, and but later we are going to relax this condition. Here we are assuming that derivative exists and is continuous, but because in the proof we are going to use Green's theorem, but we relax this condition. We don't need to assume the continuity. Just the function being analytic is enough. And remember, analytic means it has a derivative in that open domain. Okay. Any comment, any question? This is the topic that I'm going to cover on Thursday, which is Cauchy integral theorem and the consequences of Cauchy integral theorem. That is fascinating. All right, it gives you a different perspective as how beautiful complex integrations are. All right. Any comment? Any question? No question. All right, I don't see any question. Then go ahead, please. As usual, read your notes and then the text. And if you have extra text available for you, read that as well. Especially look at those examples that are done in your books, and then start doing your homeworks. All right. Don't try to do your homeworks before reading your text. So that's not a good idea. Okay. If you don't have any comment or question,